Welcome you all again for the thermodynamic lecture series. So in the previous lectures we have studied about the non-flow process and we have solved a number of problems in the non-flow process, each and individual process. But in the today's lecture we are going to solve a problem on combination of the non-flow processes. Okay, so that is considering with all the processes. So constant volume, constant pressure, constant temperature, reversible adiabatic and polytropic process. So with this combination we are going to solve the. So problem number 18, when a system is taken from a to B state. So in the figure, this is your figure. So in the figure along the path ACB, okay, so along the path AC and B, so this along the path AC and B, 84 kilojoule of heat flows into the system. Okay, so here Q of ACB is 84 kilojoule and the system does work on 32 kilojoule of work. So system does the work, so it is positive, so it is work done of ACB is 32 kilojoule of work here. Then they are asking about how much will the heat that flows into the system along the path ADB, that is how the Q of ADB, they are asking if the work is 10.5 kilojoule. So the work done of ADB is 10.5 kilojoule, then what is your heat transfer? In the second question, when the system is returned from B to A, along the curved path, so it comes along the curved path, then the work is done on the system. So here we have to note that the work is done on the system. So if they said the work is done on the system, then your work done will be negative, that is work done is equal to minus 21 kilojoule, that is work done of BA is minus 21 kilojoule here. Thus the system absorbs or liberate heat, and how much of the heat is absorbed or liberated. So here they are asking about heat transfer here, that is heat of BA. Okay, so Q of BA. The next one, if UA is 0 and UD is 42 kilojoule, find the heat absorbed in the process, that is Q of AD and Q of DB. So they are asking about Q of AD and Q of DB here. So here, considering a PV process, this A and C is through the process A and C, it is a constant volume process, and the C and B is constant pressure process, and A to D is constant pressure process, and D to B is constant volume process. Here having the combination of different processes here. Okay, so we need to find Q of ADB in the first case, and in the second case we need to find out Q of BA, and in the third case we need to find out both Q of AD and Q of DB. So how we can going to approach this problem? By using a simple first law of thermodynamics for a process here. So consider a process A, C and B. So in the first process A, C and B, I am applying a first law of thermodynamics for a process here, that is Q is equal to W plus del U. So this change in internal energy can be written as UB minus UA. So from this relation you can find it out UB minus UA, that is what all the given in the question is. So given as UCB is 84 kilojoule and work done as 32 kilojoule. So you substitute values, you can find it out UB minus UA as 52 kilojoule. That is delta U of ACB as 52 kilojoule. So with this, we need to find it out Q of ADB. So substitute. So for this process, you substitute a first law of thermodynamics. You will get Q of ADB, which is equal to W of ADB plus delta U of ADB. So this delta U of ADB can be written as UB minus UA. So here we know work done of ADB as 10.5 kilojoule and UB minus UA as 52 kilojoule. So from this one, so we substitute all the values to get the first question answer as Q of ADB as 62.5 kilojoule. So next one, I am considering the process B to A. Okay, so I am considering the process B to A. So applying the first law of thermodynamics for a process, you will get work done of BA plus delta U of BA. So we can write this as UA minus UB. So in the previous slide we find it out UB minus UA is 52 kilojoule. So I am taking one minus sign outside for my convenience for substituting the same value. So that is minus 21 minus of UB minus UA. We know that UB minus UA value will be 52. So substitute that values to get QB as minus 73 kilojoule. So the minus indicates that the system liberates heat. Then considering the process ADB. So in this process ADB, we can split and write work done of AD plus work done of DB. Okay, so that is work done of AD plus work done of DB. So with both the work done, that is total work done as W of ADB. So since work done of DB is 0, because since it is a constant volume process, though there is no area under this curve here, so you put 0 here, then your work done of ADB is equal to work done of AD. So in the problem itself, the work done of ADB is given as 10.5 kilojoule. So work done of AD is 10.5 kilojoule. Then you consider a process A to D. Okay, so consider a process A to D. You substitute a first law of thermodynamics here. Q is equal to W plus del U. That is Q of AD is equal to W of AD plus UD minus UA here. UA and UD values are given. Substitute all the values. You will get Q of AD as 52.5 kilojoule. Then we need to find Q of dB. So for that I am writing this total Q of ADB can be written as Q of AD plus Q of dB. So as we all know, Q of ADB as 62.5 kilojoule and Q of AD is 52.5 kilojoule. So with this you substitute all the values to get Q of dB as 10 kilojoule. So as a result, Q of ADB is 62.5 kilojoule in the first case, and in the second case we need to find out Q of BA, that is system liberates heats, that is minus 73 kilojoule, and in the third case we need to find out Q of AD is 52.5 kilojoule and Q of DB as 10 kilojoule. So problem number 19. So a gas occupies 0.3 meter cube at 2 bar. It executes a cycle consisting of the processes, that is the initial gas volume is 0.3 meter cube and the initial pressure is 2 bar. Here the first process 1 to 2, here we are having the three process. 1 to 2 is constant pressure process with a work interaction of 15 kilojoule. So work done is 15 kilojoule. And in the second process they have named as 2 to 3, and it is a compression process, follows the law PV equal to constant. So we know PV is equal to constant, so then it is a isothermal process or constant temperature process here. Here we are having the condition U3 is equal to U2. Then the third one is 3 to 1, it is a constant volume process. So the first one is constant pressure process, and second one is your constant temperature process, and third one is your constant volume process. Here the change in internal energy is 40 kilojoule. Here we have to neglect a change in kinetic energy and potential energy. We have to draw a PV diagram for a combination of these processes. So considering a process for constant pressure, isothermal and constant volume, we need to draw the PV diagram. Then determine the net work transfer. So net work transfer is summation of work transfer is equal to work done of 1 to 2 plus work done of 2 to 3 plus work done of 3 to 1. Okay. Then also we have to check it obeys the first law of thermodynamics or not. Okay. So with this we can draw the PV diagram. First question is we have to draw the PV diagram. Since the first process 1 to 2 is your constant pressure process, so this is your constant pressure process. Then the second one is your constant temperature process or isothermal process 2 to 3, so this is your isothermal process, and third one is your constant volume process. So we have to draw a perpendicular line to your volume axis. So this is your PV diagram. Here pressure is constant, here temperature is constant, here volume is constant here. So with this we need to find out this work done. So this area under the curve you need to find it out for this cycle. Okay, and also we have to check the net transfer is equal to net work transfer in this problem. So that is, these are all the observations I have marked from this diagram. So we know that T2 is equal to T3 because since here the temperature is constant, so we know that T2 is equal to T3. Then here the internal energy is 0 here, since there is a temperature is constant here, that is mCV into T2 minus T3, that is T3 minus T2, the both are same, so we can delta and internal energy is 0 there. Then we can observe the volume, initial volume and the final volume of this process. 1 to V1 is equal to V3 is same. And also here the work done is 0. There is no area under this curve for a constant volume process 3 to 1. So work done of 3 to 1 is 0. And we know that in the process 1 to 2, pressure P1 is equal to P2 since it is a constant pressure process. So for that, work done is equal to P into V, that is dV, that is V2 minus V1. So with this relation, I am finding out V2 here. Okay. Then I am going to apply Pvt relation for a constant pressure process. You will get T2 by T1 is equal to V2 by V1 here. So in this T2 is equal to T1 of V2 by V1. But here mass is not given and R is also not given. So we didn't find it out about T1. So you keep the relation as T2 is equal to 1.25 T1. So as we all know, T1 is equal to then Q of 1 to 2 is work done of 1 to 2 plus delta U of 1 to 2. This delta U of 1 to 2 can be written as U2 minus U1. and this u2 minus u1 can be written as mcv into t2 minus t1. Here you substitute the t2 value as 1.25 as t1 here, but we didn't know about t1 and we have no possibility to find out t1 here, so keep as the equation as q of 1 2 as 15 plus 0.25 mcv into t1 here. So consider this equation as 1, so keep as it is. Then you move to the process 2 to 3. So considering the process 2 to 3 is an isothermal process. So in this isothermal process, so we know that u3 is equal to u2. So we can write u3 minus u2 as 0. That is delta u of 2 minus 3 is, that is 2 to 3 is 0 here. Then we apply the isothermal Pvt relation. We know that P2 V2 by T2 is equal to P3 V3 by T3. Since T2 is equal to T3 here, so P2 V2 is equal to P3 V3. So in this you know P2 V2 and V3. So with this you find out P3 from this equation. Then work done for this process is P2 V2 into ln of V3 by V2. So we know all the values here. Substitute the values of work done. We find it out as minus 16.736 kilojoule for this process 2 to 3. Then heat transfer is work done plus change in internal energy. Here the change in internal energy is 0, so the heat transfer is minus 16.736 kilojoule as similar to of your work done. So Q is equal to W in your isothermal process. Then considering the process 3 to 1 constant volume process, so U1 minus U3 which is equal to, that is the change in internal energy can be written as mCV into T1 minus T3. Here we can write the T3 as 1.25 T1. Okay, so that is delta U of 3 to 1 is minus 0.25 mCV into T1. So here, so with this I am finding out the whole term because we didn't know to find out mass and CV and temperature. So you keep the term as constant mCV T1. So with this relation you find out mCV T1. So the mCV T1 value will be minus 160. Okay, so with this, here the work done is 0 since it is a constant volume process. Work done is 0 here. We need to find out heat transfer. So heat transfer is work done plus internal energy. So work done is 0. As we know, the internal energy delta U of 3 to 1 is minus 0.25 mCV T1. We substitute the value here. Thus mCV T1 value will be minus 160 here. Okay. So we substitute that values to will get Q of 3 to 1 is 40 kilojoule. So as you remember that in the first case equation 1 we are substituting keep the value as mCV T1, but in that equation you go and substitute the mCV T1 value as minus 160 to will get Q of 1 to 2. So that is, substitute equation 2 in equation 1, you will get Q of 1 to 2 as 15 plus 0.25 mCV into T1. So with this Q of 1 to 2 as minus 25 kilojoule. And also the net work transfer for the cycle will be work done of 1 to 2 plus work done of 2 to 3 plus work done of 3 to 1. So work done of 1 to 2 is 15 and work done of 2 to 3 is minus 16.736 and work done of 3 to 1 is 0 as we all know since it is a constant volume process in the case of 3 to 1. So the net work transfer is minus 1.736 kilojoule. Then they asked that we need to check for a first law of thermodynamics. So you need to find out summation of heat transfer, that is Q of 1 to 2 is plus Q of 2 to 3 plus Q of 3 to 1. Substitute all the heat transfer values to will get the net heat transfer as minus 1.736 kilojoule. So since it is proved that the net work transfer is equal to net heat transfer here, so it obeys the first law of thermodynamics. So as a result, the first one they asked to draw the PV diagram, and second one the net work transfer is minus 1.736 kilojoule, and in the third one we have proved that the net work transfer equal to net heat transfer since both the values are same in this case. Then problem 20, the 3 grams of nitrogen gas at 6 atmosphere, that is 3 grams of nitrogen, here the mass is 3 gram, so convert into kilogram. The nitrogen is given, nitrogen is a gas, okay. Then 6 atmospheric pressure, so we need to consider 6 atmospheric pressure and 160 degrees Celsius, temperature is 160 degrees Celsius, so 6 atmospheric pressure will be converted into normal 6 into 1.01325 bar, okay. With the piston cylinder device is expanded adiabatically. So here in the first case it is expanded, it is an adiabatic process to double its initial volume, so that is V2 is equal to 2 times of V1 here. So here the first process, your adiabatic process. Then it is compressed at a constant pressure process. Okay, so then it is a constant pressure process, it is compressing to its initial volume, then compressed again at a constant volume process. Here we are having 3 processes. In the first process, that is reversible adiabatic process, and in the second process is constant pressure process, and the third process again constant volume process. Calculate the net work done on the gas. Here also we need to find out work done on the gas here. Draw the PV diagram for the process. Take Cp value here. Okay, so net work done we need to find out, that is work done of 1 to 2 plus work done of 2 to 3 plus work done of 3 to 1 here. So these are all the given data here. So here I am taking as MN2, that is molecular mass of nitrogen as 28, that is N2 as 28. For nitrogen it is 14, for N2 as it is 28, and 3 gram is converted into kilogram, that is 3 into 10 to the power of minus 3 kilogram, and 6 atmospheric pressure is converted into normal, that is 6 into 1.01325 into 10 to the power of 5 Newton per meter square. And temperature into Kelvin, the initial volume V2 is equal to 2V1. As we all know, since it is a constant volume process, so we can say V3 is equal to V1 here. So as a result, first they have draw about PV diagram. So in the first process is your reversible adiabatic process. Okay, so reversible adiabatic process, and 2 to 3 is a constant pressure process. Here they have said as expansion, so the volume will be increased here. Okay, so it is a reversible adiabatic process, and it is a constant pressure process, compression. And 3 to 1 is your constant volume process. As we all from the diagram we can know work done of 3 to 1 is 0 here, since it is a constant volume process. So in this case we need to find it out work done of 1 to 2 and work done of 2 to 3. So with this given data, first one we can find it out R as RU by M. R is your universal gas constant 8314, and your molecular mass of nitrogen is 28. So with this R is equal to 297 joule per kilogram Kelvin. Then with this ideal gas equation, P1 V1 is equal to MR T1, you find it out V1 here, that is 3 into 10 to the power of minus 3 as mass, R 297, and temperature 433 divided by your volume, sorry, pressure. Then you will get the volume as 6.3 into 10 to the power of minus 4 meter cube. Then your R is equal to Cp minus Cv, so we know R and Cp is given in the question, so you find it out Cv here. Since 1 to 2 process is your adiabatic process, so you need to find out gamma here. So gamma is Cp by Cv. So you substitute Cp from a given data and Cv from this relation, you will get gamma as 1.4 here. So consider process 1 to 2 as an adiabatic process. So T2 by T1 is equal to V1 by V2 whole to the power of gamma minus 1. So with this, we know that the initial volume V2 has 2 times of V1. So substitute that, you will get T2 as 328.15 Kelvin here. Then work done of 1 to 2 is for an reversible adiabatic process, MR into T1 minus T2 divided by gamma minus 1. So we find it out gamma from the previous slide, substitute all the values to will get work done of 1 to 2 as 233.55 joule. Then considering the process 2 to 3 is constant pressure process, so applying the Pvt relation to will get to find it out T3. Okay, so that is T3 is equal to T2 into V1 by V2 times of V1, so we can cancel both the V1, so we'll get 1 by 2, that is temperature T2. Then T3 is equal to 328.15 into 1 by 2. As a result, T3 is 164.07 Kelvin here. So work done for a constant pressure process, MR into T3 minus T2. So as we all know T3 and T2 from the previous one, so the work done of 2 to 3 is minus 146.19 joule. So since it is a constant volume process, I already discussed the work done of 3 to 1 is 0. There is so no area under the constant volume process here. So the net work done formula will be work done is equal to work done of 1 to 2 plus work done of 2 to 3 plus work done of 3 to 1 here. So substitute the values to will get the net work done as 87.36 joule. Sorry, 87.36 joule here. So as a result, they asked about net work done of the gas, 87.36 joule, and they asked to draw about the PV diagram. Okay. Thank you.